Problem 4.55. In this problem, we have a temperature that exhausts from a pipe that is it's approximated by the given equation, where T0 is equal to 100 Celsius, A is equal to 3, B is equal to 0.03 meters to the negative 1, C is equal to 0.05, and omega is equal to 100 radians per second. If the exhaust speed is given to be 3 meters per second, we need to determine the rate of change of the temperature of the fluid particles at x equal to 0, x is equal to 4, while when the time is equal to 0. Okay, so let's just start with the information that is provided. So they gave us a value for the temperature, so it's T0, 1 plus AE to the negative BX, and this is 1 plus C cosine of omega T. They gave us different values, so for temperatures we're gonna just keep those values, and we're gonna do it in symbols rather than substitute it just yet. Okay, what we need to find is the rate of the temperature change, and we have to do it at x is equal to 0, x is equal to 4, while the time for both is equal to 0. We are going to assume for this case that this is going to be transient. Notice that the function that we have is a function of time, and we're going to take it to be only one dimensional since we don't have any other variables inside of here. So we're going to start by writing the rate of change of the temperature as a function of time. So this is going to be partial derivative of t with respect to t plus u dt dx plus v dt dy plus w dt dz. Since it's one dimensional, we're able to get rid of the last two terms. And we're gonna need the derivative with respect to time and derivative with respect to x. Okay, so if we take the derivative with respect to time, we find this to be negative T0 times A times C times omega e to the negative bx times sine of omega t. And then if we take the derivative with respect to x, we find that to be minus T0 A B e to the minus bx times 1 plus C cosine omega t. Okay, so I'm just gonna make this a little bit bigger and then substitute. Okay, so we're gonna take all these values and we're gonna substitute into this equation. So we find that the t dt is going to be the derivative with respect to time, so it's gonna be minus T0 A C omega minus bx sine omega t plus, and then the velocity u, in this case it was given to be 3 meters per second, so it's 3, it's a constant, and then we write the partial derivative of t with respect to x, minus T0 A B minus e to the minus bx, and then multiply this with 1 plus C cosine of omega t. Oops, almost didn't fit. Okay, so notice that we're going to evaluate both of them at time equal to 0, so to simplify it, so this terms will disappear. Okay, and we evaluate sine at time, cosine of 0 will give you 1, and then sine of 0 will give you 0, so these terms will disappear. So at the end, the t dt, and once again we're evaluating at t equal to 0 since the position is different but the time is equal to 0, so we could just write it at minus T0 A B e to the minus bx c plus 1. Okay, so basically it's only this term, and then we replace by the quantities that we have. So we had T0 was equal to 100 Celsius. Okay, and then we go back to the values that we had from before. So we have T to be equal, T0 is equal to 100 Celsius. We had A to be equal to 3, B is equal to 0.03, C is equal to 0.05, and then we got omega is equal to 100. Okay, so we're gonna bring it back and substitute into this equation with the two different values that we had for x. So at x is equal to 0, if we substitute all these values and x is equal to 0, dt gives you minus 28.35 Celsius per second. And if we do the same process at x is equal to 4, dt is equal to minus 25.14 Celsius per second. So what that means is this. So imagine that you have your pipe, right? And at time equal to 0, both of them, so this is position at x is equal to 0, and this is x is equal to 4, right? So we're gonna just have that pipe, and then we're gonna just do exactly the same pipe on the side over here. So this is exactly the same pipe that we have, right? So we have position 1 and position 2. So at time equal to 0, the temperature over here was 100 Celsius, and the temperature over here is 100 Celsius. What this indicates is that you're gonna have this amount of drop per second. So what we could say is at time equal to 1 second, at position 0, instead of having 100, you're going to have 100 minus 28.35, and so that is going to give you 71.5. So in this position, you're going to have 71.5 Celsius. And in the second position, what you're going to have is going to be 100 minus 25.14. So in this temperature over here, at this position, you're going to have 74.86. So what it's telling you is that the change of the temperature that you're going to have in the first position is going to be significantly higher than what you have in the second position. So the further that you are, the closer that you are to the entrance, your temperature is going to drop faster than what you are if you're farther away from the entrance of the pipe. This is what this quantity tells you.